Hi. In the previous week, starting from lecture number 5, we saw this Efron-Stein bound which controls the variance of random variables. It allows us to divide the variance of a random variable, which is a function of multiple independent random variables, into variances associated with individual components. And that bound can be viewed as some bound for controlling the variance itself, but it has other implications. For example, last week we saw the Gaussian-Poincare inequality, where this Efron-Stein bound was used to complete the so-called tensorization argument. Namely, it was used to boost the argument for n equal to 1 case, one-dimensional functions with one-dimensional input, to the general n case, namely functions with n-dimensional inputs. And today, in this lecture, what we will do is we will use Efron-Stein for a similar tensorization argument, but this time towards deriving concentration bounds for random variables. So we have already seen several concentration bounds, and before I proceed with what I want to say for Efron-Stein inequality, let me quickly review the general recipe, sort of a general recipe for deriving concentration bounds, which we have been following till now. So how to derive concentration bounds. Okay. So till now we have seen the Hofting bound, Hofting's inequality, and we have seen several others. We have seen Bennett's inequality, and then we have seen McDiarmid's inequality. Okay. In fact, McDiarmid's inequality, the proof, it doesn't really require the random variables to be independent. It requires them to be. It doesn't require any assumption about the random variable as such. It requires that we have a function of the function satisfies certain bounded difference property, and then we use the multiplicative family formed by conditioning, and we derive some inequality. But if you look at so this is a slightly different proof, slightly different, not too far from the recipe that we'll describe. But these first two bounds basically follow a general recipe. So let's look at what we did. Just let's recall what we did for deriving Hofting bound. So there were two steps involved in deriving Hofting's bound. Step 1 was what we called Hofting's lemma. So here what we saw was that if you have a random variable x that takes values in a and b, then it's log moment generating function. Okay, let's look at the centralized log moment generating function. So phi of x minus expected value of x of lambda we saw is less than equal to lambda square by 8 b minus a square. Okay, that's what we showed. And in fact in showing this we yeah, you can just assume x is 0 mean here, but in showing this what we noticed was that this function phi, this function psi, the log moment generating function, its derivative at 0 is 0. I'm just omitting the subscript here because it's fixed throughout, and its second derivative at lambda can be written as a variance of x under some appropriate measure, some other thing, let's call it q lambda, something depending on lambda. Okay, and we know that variance of bounded random variables are bounded, and we use that. There are other proofs of this as well, but we somehow examined some analytical properties of this function, and we got a bound on this. And the great thing about this bound is that if you have it for one dimension, then it extends to n dimension in some way. So step 2 was what we can call a tensorization argument, which is the argument tensorization arguments, which is the arguments we made to extend this bound to general n-dimensional random variables. In the case of Hofding bound, in the case of Hofding's inequality, what we did for tensorization was use subadditivity of sub-Gaussianity parameter, the variance parameter. So here is the claim we were using. If independent random variables x1 to xn are such that xi is sigma I square. So I think the language we have been using is sub-Gaussian with variance parameter sigma I square, and this is true for I between 1 and n, then summation I xi is sub-Gaussian with variance parameter summation over I sigma I square. Okay, this is some property of sub-Gaussian random variable. So this argument allowed us to extend the bound that we have for one dimension to bound that we have for n dimension. We only have to add this bi minus ai now. Okay, so all the proofs that we have seen, even Bennett's inequality has this two-step approach. First, we show some bound for the log moment generating function in some way, and the way that bound is established, the property, for instance, it's a sub-Gaussianity bound here, that property can be tensorized. Okay, this the second part is some tensorization argument. So if you establish a sub-Gaussian bound, it tensorizes. If you establish a sub-Poisson bound or sub-exponential bound or sub-gamma bound, it again tensorizes. So I think for Bennett's inequality, we saw a sub-gamma bound with appropriate parameter, and that bound also tensorizes. This is a general two-step approach that we have been showing. So to summarize, the general recipe that we have been following. For deriving concentration bounds is the following. So step 1, establish a property that implies a bound for the log moment generating function. Okay, so for example, for Hofding's inequality, that property was boundedness property of the random variable. Step 2, show that that property tensorizes. Okay, and how do we show that this tensorization? Yeah, that's not obvious. In fact, when you are trying to identify this property, you will look for properties which tensorize, and that's how these proofs are completed. So I just want to highlight this general recipe because throughout the course we will essentially follow this general recipe, and what we will see is a lot of very cleverly crafted properties so that they tensorize well, right? That will be a general recipe. So with this general recipe in our mind, we can now what I'll now present is how you can use the Efron-Stein inequality to establish a concentration bound. Okay, this is the main topic of this lecture: concentration bound using Efron-Stein. Okay. So we'll have to do two things, as we said. We first have to identify this property, and then we have to see that that bound tensorizes. The tensorization part we will see will follow from Efron-Stein inequality. Okay. But before that, let's look at the bound that let's maybe uh, yeah the I'll state the theorem and then I'll show how it can be proved using Efron-Stein and how it can be proved using this recipe. But if you want to deconstruct the proof, first you have to identify the property. That's the main observation, and then you tensorize, and then this theorem comes out. Verifying is easy, but coming up with this theorem is very difficult. Okay, so what's the theorem? Well, verifying is not so easy itself, but at least it can be structured. Okay, so once again you are given this random variable z, which is a function of x1 to xn, and these guys are x1 to xn are independent. And what we assume about these guys is some sort of bounded difference property, but we'll write it in a compact way. So let's the zi prime be f of x1 to xi minus 1, and then you replace xi with its independent copy and xi plus 1 to xn, where x1 prime to xn prime is an independent copy of x1 to xn. Okay, so you define these guys and you define this for every I between 1 and n. That's what we define. Yeah, so if you can recognize these guys from our Efron-Stein inequality, where we had a similar independent copies coming in. So what we assume is that suppose that summation I equal to 1 to n z minus zi prime square, and let's just take the positive part of it. Remember, from symmetry we can have this term showing on the right side of Efron-Stein inequality. This guy is less than equal to v. So this is sort of the proxy for the variance that we have. So this is the assumption. So a side remark here. Satisfied with v equal to ci square for f that satisfies, for f satisfying the bounded the C1 to Cn bounded difference property. Okay, so if f satisfies the C1 to Cn bounded difference property, then this assumption here holds with v equal to summation ci square. This is essentially equivalent to this bound, nothing more. Okay, this is essentially equivalent. It's not more general or less general. Okay. So we just keep it in this compact way, and this will help us later on as well. We'll use this compact notation here to summarize this bounded difference property. So suppose this holds, then probability that z exceeds the expected value of z plus some t, too many pluses and t's here, plus some t is less than equal to 2 times e to the power minus t by root v. Yeah, so this is a slightly different bound from what we had seen earlier. Earlier, using McDiarmid inequality, we had seen a bound which looks like, I think, t square by summation ci square, so t square by v, t square by 2v, something like that. Now we see t by root v here, and depending on where the t is, this can be better or worse. But in general, the McDiarmid bound is a better bound than this one. But we'll give a different proof of this bound. We'll use Efron-Stein inequality to come up with this bound, and we'll illustrate the general recipe we pointed out. Okay, so this is interesting. We bound a variance, and somehow from that we can bound the log moment generating function. This is sort of a bound on log moment generating function. And the question is, how do we translate this variance bound to a log moment generating function bound with roughly the same variance parameter? By the way, note that this is only e to the power minus t by root v, so it's the so-called sub-exponential bound rather than sub-Gaussian tail bound. Um, but that's okay. We are getting a weaker bound, but the purpose here is to illustrate a recipe. Okay. So let's try to prove this. The proof follows our general recipe, as we outlined above, where we start by defining a property which will lead the bound for log moment generating function, and that property will be such that it tensorizes. So we consider this random variable y defined as the one which we use for defining log moment generating function. Just normalize by 2. That's just for convenience. We'll see how it plays a role. Then variance of y is equal to the expected value of this guy. This is the moment generating function. Okay. Square of this. So that's just this guy here minus the expected value of this guy whole square. Okay, that's what variance of y is. Okay, and the property is the property we want to prove. This is sort of a claim, I'm putting it down here. If variance of y is less than equal to lambda square by some constant, we'll get 4 v, and then into, let's say, expected value of e to the power lambda. So suppose you can show that, then we can derive a nice bound for the log moment generating function. Then is less than equal to maybe we write a simpler implication of this bound, then is less than equal to a constant. That's the claim. So if you have this bound, then you get a bound like this. By the way, so why do we want a bound like this? So this in particular implies that if you look at the probability that c minus ez is greater than t, just using Chernoff boundary, then this guy is less than equal to we have this bound for log moment generating function. So this is less than equal to expected e to the power lambda times e to the power minus lambda t, and if we choose lambda equal to 1 by root v here, then if we choose lambda equal to 1 by root v here, then what do we get? This is less than equal to e to the power but this guy is a constant, and this guy is less than equal to 16 by 9 e to the power minus t by root v. 16 by 9, this is this log is the log that we have here. Yeah, so that's correct. So we get this bound. So any constant here, you will get the same constant lambda, and you get the same e to the power minus t times that constant bound. This is also called a sub-exponential bound. So it suffices to find a constant lambda, in this case, which is 1 by root v, for which the log moment generating function is constant. If you have that bound, then my Chernow bound, you will get a sub-exponential bound with the same constant. So this part is easy. So it will give a desired result. I put down 2 there. You can get 16 by 9. But that constant is not important for us. Okay, so this property is essentially what we want to show. So if you have this property, then you get the desired concentration. That's the claim. So first part, that how do we show this property? Where v, remember, is the bound here. That's the first part. That's the first question that may come to your mind. We'll come back to this question later. In fact, this is where we will use tensorization. We will show that this property tensorizes because of Efron-Stein inequality. But before we show that, let's first convince ourselves that indeed this property is the one we want to show. Okay, so what's the proof of this claim? So proof of the claim. So to prove this claim, what we note is that this variance of y is equal to expected value of e to the power lambda, this term, minus expected value of e to the power lambda by 2 whole square outside. Okay, this is just what variance of this. And this we are claiming is less than equal to lambda square by 4 times v times the same function here. Okay, if you have this, then you can take this on the one side, take this on this side. This guy is less than equal to expected value e to the power lambda by 2 whole square. Okay, that's what that property implies. We define this guy here to be something. Let's call this maybe f lambda. Maybe I should call it just g lambda. Not sure where I've used this f. F is already taken. F lambda, and this guy, if you notice, is g lambda by 2 square. Actually, it's better to first take the log and then define this function. Okay, so let's take a log here. So this is if and only if the log moment generating function plus log of 1 minus lambda square by 4v is less than equal to the same log moment generating function at lambda by 2, but there's a factor of 2 outside. Okay, so that's what the property that we are assuming here, this if part here, this property is equivalent to having this condition here for the log moment generating function. So this is a functional inequality for the log moment generating function. And then this property, by the way, we are assuming this one holds for all lambda greater than 0. Okay, so this one here is for all lambda greater than 0, greater than or equal to 0. Okay. So once you have this property, what we are claiming is that this sort of implies some bound for this function itself. So Let's just define this guy here. This guy here for convenience, we define it as g lambda. So suppose you have g lambda is plus some log 1 minus lambda square by 4 v some constant is less than equal to 2 g lambda by 2. From that can we get a bound for g lambda. So we keep on repeating this. This implies if we repeat it k times, this implies g lambda is less than equal to minus summation I equal to 1 to k log of 1 minus lambda square by 4 into 2 to the power 2i times v plus sorry about this. Let me just try to think of this multiple each step. Let's do this slowly. So g lambda is less than equal to this. So g lambda then is also less than equal to, now I'll apply it once again to this function here because it holds for all lambda greater than 0. It's less than equal to 2 times. I'll substitute the same thing here. G minus log 1 minus lambda square by 4 into 4 because now it's lambda by 2 times v and plus 2 into g lambda by 4. Okay. And then you can apply it again. Every time you apply this inequality, you get an extra factor of t. You get an extra factor of 2 with the log term, and you get an extra lambda by 2 here and this extra factor of 2 outside. So when you apply it k times, what you get is this is less than equal to equal to 1 to k 2 to the power I log of 1 minus lambda square by 4 2 to the power 2i times v plus 2 to the power k plus 1 lambda by g of lambda by 2 to the power k plus 1. Okay, that's the one. Okay. Therefore, what we have is that g lambda is less than equal to summation I equal to 0 to k 2 to the power I log of 1 minus lambda square by 4 2 to the power 2iv plus 2 to the power k plus 1 g lambda by 2 to the power k plus 1. So when we take this k to be very large, as we take the limit k going to infinity, what happens to this guy? This guy here. So taking limit k going to infinity, the right side equals, so there are two terms. The first term, I'll come to it later, limit k going to infinity of this guy here plus limit k going to infinity of this second guy. So the second guy is 2 to the power, so I'll take a lambda out, so it looks like this, lambda by this by lambda by to the power k plus 1. So what is this guy? So as k goes to infinity, this goes to 0 from the right side, and this function g, so this is g of sort of g of x minus g of 0 by x in the limit as x goes to 0 from the right side. So this guy here is just g prime of 0. Okay. So this guy here is just that, g prime of 0. So this limit here is equal to g prime of 0. But remember, our function g was this guy here, and we are taking its derivative with respect to lambda and putting it at 0, and this is a central, this is a 0 mean random variable, so this guy is also 0. Okay, so this term here is 0. Therefore, what we have is the bound that we have obtained is that g lambda is less than equal to minus summation I equal to 0 to infinity 2 to the power I log of 1 minus lambda square v by 4 2 to the power 2i. Okay, that's what you get. So we can express this sum here as minus summation I equal to 0 to infinity That's how you can express it as. And the reason I'm doing it this way is the following. So now if you look at this function here, this has this form of 1 by u log 1 minus xu, and where u is a number between 0 and 1. So let's plot 1 minus log of 1 minus x, okay, for x between 0 and 1. This log of 1 minus x, how does it look for x between 0 and 1? So this guy at actually minus log, there's a minus sign here, I'll take that minus inside, right? So this, I'm just writing this as u is some number between 0 and 1. So at x equal to 0, this is 0, and at x equal to 1, this is infinity. So minus of that, so it looks like this. That's what this function looks like. So as you take this u from, this is log of 1 minus x. Now what we are doing is we are parameterizing a point xu, and we are looking at this line here. We are using bigger graph and different color, so we plot this function. Just want to notice a very simple inequality about this function. 1, and then I take 2 points. I'll take this point here, xu, and draw this chord. It lies above the function because, as you can see and verify, this is a convex function. So if this lies above this function, then this guy here, this log of 1 minus xu minus log of 1 minus 0, which is just 0, so minus 0 by u minus 0, Actually, what I would like to do is I would like to plot log of 1 minus xu as a function of u, and so for u between 0 and 1. So this function now will truncate at a particular point. Let's see where it truncates. So again it looks like this, but it stops here, which is at 1 minus x, and at this point its value is log of 1 minus x. Now you take any point. This is the point x, this is the point some arbitrary u, and draw this line. This will also lie above it, and the slope of this chord is this much. And because this function is concave, as you increase u, what happens as you increase u? As you increase u, this chord, its slope increases. Okay, and so this slope is less than equal to the slope at u equal to 1. So this guy here, this function here, the inequality I have roughly argued is this is less than equal to log 1 minus x for all u between 0 and 1. Okay, that's the bound you have for this function. Therefore, this guy here is less than equal to summation I equal to 0 to infinity 2 to the power minus I, and what you have here is log of the minus outside, log of 1 minus x. X for me is lambda square v by 4. Okay, and this summation here now is easy to sum. This just sums to 2. So this is equal to 2 times log of 1 minus lambda square v by 4. So in particular, g of 1 by root v is equal to minus 2 times log of 1 minus 1 by 4. Right, so that's log of 16 by 9, as I said. Okay, that was the claim. So this is just the proof of the claim. So let's go back to our claim. Okay. So we had this nice intermediate step that if you can show this bound, then this function is less than equal, the log bound generating function is less than equal to log 16 by 9, and it uses a functional inequality in the middle. Okay, and this is some property. This is like replacing the Hofding lemma with something else. So this is a replacement of Hofding lemma. And now comes the second part of the proof, namely the tensorization step, which says that this property, proving this property for one dimension is the same as proving this property for n-dimensional things, and that's what we will do through we'll show this property through the tensorization step will be provided through the Efron-Stein inequality. So let me do the next step now, the tensorization step. So by the Efron-Stein inequality, variance of y is less than or equal to variance of, so y again is a function of those x1 to xn, the independent random variables. So we can apply that inequality to this function as well, and what you get is it's less than equal to I equal to 1 to n expected value of y minus yi prime. So now remember that what is yi prime? Yi prime is equal to e to the power lambda by 2. The function was z minus expected value of z, and so this will become f of xi minus 1 xi prime xi plus 1 to n minus expected value of z. Yeah. That's what this quantity here is. And y minus y prime square, and there is a factor of half. And if you use symmetry property, you can just write it as the positive part. This is just the positive part of a number. Okay, this is by now Efron-Stein. Okay, so this is still not bringing in the v part, but at least the tensorization property holds. Now we have to handle just a one-dimensional function here, which has a similar form. You can think of this entire thing as that function for a fixed x1 to xi. Okay, now we notice an elementary property. It's a simple bound for e to the power lambda x, small x, is less than equal to. So if you look at e to the power lambda x minus e to the power lambda y by Taylor series approximation, this is less than equal to the first order Taylor series approximation. Max over theta in let's say x comma y. We're just assuming x is smaller than y. Okay. So max over theta in x comma y, if x is smaller than y, derivative of this guy times x minus y. But what is the derivative of this guy? The derivative of this guy is lambda e to the power lambda theta. Right? And again, e to the power lambda theta is increasing function of theta. So this is less than equal to x minus y into lambda into e to the power lambda y, because I'm assuming x is greater than y. Sorry, y is greater than x. Right. So we can use this inequality here, and this inequality here implies that y minus yi prime square is less than equal to, so now I'll just have x minus y, this exponential part will go away, z minus zi prime plus square, and I'm working with lambda by 2, so this becomes times lambda square by 4, and this remains the same guy, this remains y. Okay, so this is that magical inequality we were looking for. This becomes y square actually, because I squared this inequality into this. Okay. Therefore, expected value of y minus yi prime square is less. This is the fundamental inequality which tensorizes using Efron-Stein inequality. The fundamental inequalities for each coordinate is less than equal to summation I equal to 1 to n expected value of z minus zi prime square lambda square by 4, and this is just expected value of y square. Combining both the bounds, what we get is variance of y is less than equal to expected value. I'm just taking this expectation out. Times lambda square by 4, and this guy, this is by definition, this is the function expected value of lambda z minus expected value of z. Okay, that's and by our assumption this guy here is less than equal to v, the variance factor. Therefore, what we have established here is this assumption of this claim that variance of y is less than lambda square by 4 v times this function. And in establishing this, we essentially had to establish this for one dimension part here. If this holds for one dimension part, okay, then it automatically holds for n dimension by the Efron-Stein inequality. So we just had to show this bound for one dimension. So this is the tensorization step, which can be shown for n dimensional. So this completes the proof, and the important point to notice here is how we proved this. The recipe itself. The magic was in identifying this property, this particular property, that sorry, the property in the claim, this one here, and it's this property that we identified. This property yields a bound for this. That was the good thing about this property, and it tensorizes. Okay, so a large part of literature of concentration bounds is around identification of such properties, which will yield a bound on log moment generating function and tensorize. We have already seen that subgaussianity is one such property, and that's a bound which tensorizes. And this version is more abstract. Here we ask for a function inequality, and when it holds, it implies a bound for the log moment generating function, and it tensorizes. Okay. And this tensorization for this particular bound, this sub-exponential bound that we finally attained, this one here, this tensorization relied on the Efron-Stein inequality. So that's what we wanted to show, that the purpose of introducing this part was actually to, as a segue to the next part, where we'll talk about the entropy method, where this particular property here, the variance of y bounded in this way, this property will be replaced with some other property of the log moment generating function, a function inequality, which we assume holds. And when that function inequality will hold, we'll get another bound for the log moment generating function. And this is the so-called Herbst argument, and it will lead to the entropy method. That's what we will do in the next lecture. Okay, see you in the next lecture.